The Constitution of India. Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, my dear children. I hope you all are doing good, getting prepared for your exams. I think you must have set a timetable for preparing for your online exam. Don't get afraid, children. I know my children are very strong enough to face it. So wish you good luck. Have a good preparation, focused study. Definitely you will do well. Okay. I'm here to share a small story to you. It goes like this, children. There was a mother and a son who was studying in 7th standard. This mother used to work in different houses to make a living, and the son who was studying in the school used to carry lunch box which is offered by his mother daily to his school. But one day there was no rice in the house, so she couldn't make anything for her son. So he went to school without the lunch box. The mother was very upset. Soon she went around the houses, collected some rice, prepared food, put it in the tiffin box, and then she carried it to the school. And when the classes was going, she didn't bother to get inside the class. She just went inside, she kept the tiffin box on the table and came out. This mother was having only one eye, right? She could see only with one eye. So when she entered the classroom with the tiffin box, the classmates, all the children made fun of her, and they started realizing that this boy is the son of a one-eyed woman. They started making fun of his mother. But he didn't make it a big issue. He just kept silent. After a few days, when he was walking in the ground, there was one boy who criticized him very badly and made fun of him. So this made this boy very much upset. He got angry. He threw a big stone on that child's face, and it was just bleeding around. So this boy got upset. So he was panicked that he will be caught. So he didn't tell his mother. He just went out of the village, and he took few vehicles, got lift, and then he reached a city. There he worked hard, just like in movies that we saw. He was working very hard. He soon turned into a very big businessman. But then what happened? Soon when he became popular, in all the articles his name was written, and in one of the articles he has mentioned about the school till 7th standard he has studied and about his principal. So the school management was surprised to see their name in the paper. They soon invited him to the school for felicitation, and when he came, he was very happy to be in his village, and then he had a feeling that he wanted to see his mother and his home. But when he went around the place, it was totally changed. So he went to his place where he was staying. There was a different house. An old man was sitting there. And when he went close by, that old man asked this boy, "Who are you, my dear?" But this boy replied, "I am the son of a lady who had only one eye. She was living in this house." But this man realized, he said, "That lady is no more, my dear. But she knew that you will be coming back, and she has offered a letter for you." So he took the letter very soon. He went inside the house and he was reading the letter, and it goes like this: "My dear son, I'm very happy and I really know that you will be coming back and you will be reading this letter. We were actually living in the city, and when you were 2 years, you lost your father in an accident, and then when you were playing with a toy, when you were small, it got hurt. One of the toy hurt your eye, and that's how you lost one of your eyes. And when I went to the doctor, he said your eye can be replaced with mine. So I was very happy that I can give my eye to my son. And for the surgery, we had to give our house and some of the properties. And after the surgery, we came back to the village. And that's how I lost my eye. This I have not told to anybody in our family. And when you come back, I know, though I couldn't see you now, definitely when you see yourself in the mirror, I will be seeing you through my eyes. So I'm so happy for you, my son. Take care. So children, why I want to say this is, there are two persons in our life who are permanent, who will not change and who are ready to do anything for us. Their love, their care, everything is true. They are the blessings for us. They are the people who are selfless. Try to love them, try to be with them, take care of them, spend most of the time with them, because they are the priceless stones, valuable gems for us, who guide us in our life. They are nobody else than our parents. Both mother and father play a very important role in our life, children. So take care of them, spend time with them, be happy, right? Maximum you try to share with them, because they are the best friends in our life. Then comes anybody in your life who are not permanent. So these permanent blessings are very, very important. I know my children will do that. Never go against their words, because they know what you want. So take care, children. Okay. So with this, let us begin our today's class. Last class we were learning about shapes of atomic orbitals, sp, df. Today we'll see about, you were seeing the videos where you got to know about px, py, pz, dxy, dyz, dz square. Remember, children, you might be seeing in the video. In that we have the place where the probability of finding the electron, sometimes it can even become zero, the density becomes zero. Such places we call it as the radial nodes. This comes only in 1 mark. They never ask you to derive or explain more than that. It comes just in 1 mark question. For ns orbital, for example, if 2s orbital is given, it is 2 minus 1, which is only 1 radial node. So for ns orbital, it will be n minus 1 nodes. Apart from this s, when you come to p or d orbital, there will be more and more of intersection, because it is dxy, dyz, so there will be an intersection. So such nodes we call it as angular nodes. In s orbital, it's just a spherical shape, there is no intersection of axis. But here in d and p orbital, we have angular nodes, which is denoted by L, which is n minus L minus 1, which we call it as a radial nodes. This again comes in 1 mark. The notes for this I will be giving to you separately. That is the HSS live. I will take a screenshot and I will send it to you. That is more than enough for you to learn, because in your textbook, apart from what we want, extra things are given to us. Okay. Now when you come to energy of the orbitals, when you say s orbitals, I told you it is spherical in shape. So the electron density is all over spread, right? But when you come to p and d orbitals, we have like this. When I say p subshell, 3 orbitals are present, d subshell, 5 orbitals are present. An electron present in every single orbital will be having the same energy. Such energy we call it as degenerate energy. Degenerate means having equal energy. So these are in the ground state. Ground state means at lower level. But when they get some energy and when they get excited, they get into a higher energy level. So that we call it as an excited state. So energy will be same here, but when they go to a next level, they may gain some more energy. That is what we studied in hydrogen spectrum, right? So what exactly happens with this? See, when I say nucleus, this is an atom. I have my nucleus in the center. These are my orbits where the electrons are revolving around. But what happens here? The outermost electron is not getting an effect of this nucleus. Why? The electron which is present closer to the nucleus is being attracted by the nucleus. The next orbit to some extent. But the electrons which are present in the outermost shell are not getting enough attraction with the nucleus. What could be the reason? This is called as screening effect, or we also call it as shielding effect. What do you mean by shield? Like if you are there and I am here, if I put a sheet here, or if I put a cupboard here, I will not be getting your attraction, or I cannot see you. You will be screen guarded, you will be shielded. So these electrons which are present in the outermost orbit are getting shielded or not getting attracted to the nucleus because of the electrons which are present inside. Such effect we call it as shielding effect or screening effect. And this nuclear charge we call it as effective nuclear charge. So the effective nuclear charge is nothing but nucleus giving an attraction to the electrons which are present in the orbits. So if that is not happening properly, what happens? As the atomic number increases, the number of shells will increase. So when number of shells increases, the shielding effects becomes more, right? The electrons are less attracted by the nucleus. That's why we said ionization energy becomes low. So this is with respect to the effective nuclear charge, which is given in page number 57 for you. Shielding of the outer shell electrons from the nucleus by the inner shell electrons. Such are called as effective nuclear charge. Energies of the orbitals in the same subshell decrease with increase in atomic number. In the same subshell, what happens? When the atomic number increases, the energy will decrease because they are not getting the attraction with the nucleus. So they will have only less energy, so they can be easily removed. Now we will get back into filling of the electrons in the orbitals, where we have three important rules: Aufbau's principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity, which we will see one by one for filling the electrons in the orbitals.
Okay, now we will see about how to fill the electrons in the orbitals. I told you there are three simple rules which will be helping us for filling the electrons in the orbitals. The first one is Aufbau's principle. Aufbau means building up. We are going to build up the orbitals one by one. How do you build up the orbitals? By filling the electrons in each orbital. So the rule states like this: the orbitals are filled in the order of their increasing energy. That is, it will be filled only with the increasing order of their energy. If you remember, children, in 10th standard we were studying about 1s, 2s, 2p, 3s, 3p, and after 3p 4s comes. Then only 3d comes, because energy level of 4s is low as compared to that of 3d. If you can recollect what we have learnt in 10th standard, this is the increasing order of their energy, and we also know S subshell can take 2 electrons to the maximum, P can take 6, and D can take 10 electrons, and F can take 14 electrons. This is the increasing order of energy. In the first energy level we have 1s, after that second energy level we have 2s and 2p, in the third energy level we have 3s, 3p and 3d, but before 3d 4s should come because the energy level of 4s is low as compared to 3d. So this is an increasing order of their energy. So depending on the atomic number, we will start filling the electrons, which we will be doing once we finish all the rules. The next one is Pauli exclusion principle. Now what does this rule states? No 2 electrons in an atom. No 2 electrons in one atom, any 2 electrons if you take, cannot have the same set of 4 quantum numbers. How many quantum numbers we have? 4 quantum numbers. Principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. If you take any two electrons in an atom, they will not be having the same set of 4 quantum numbers. So the rule is reframed in a way only 2 electrons may exist in the same orbital. Any orbital I take, say we know S subshell has 1 orbital, P subshell has 3 orbitals, D subshell has 5 orbitals and F subshell has 7 orbitals. So any one orbital that you take, only 2 electrons can exist. You can fill only 2 electrons in one single orbital, and these electrons must have opposite spin. What is spin? Spin quantum number we studied. It is helping us to know the orientation, that is the rotation in which side, whether it is clockwise or anti-clockwise. So if I am going to put an up arrow in one, the next one should be a down-headed arrow. So they should be having opposite spin. If there are 2 electrons in an orbital, their n value, L value, M value can be same, but their S value should be different. Both you cannot fill in an orbital both electrons like this or both down-headed. It is completely wrong, does not make any sense. So children, be careful when you are filling the electrons in the orbitals. And what is the formula? It is 2n square. Giving the value of the principal quantum number n, you can find out how many electrons can be filled in a particular atom. So these are the 2 principles, or these are the 2 rules that helps us to fill the electrons in the orbital. The third one is Hund's rule of maximum multiplicity. So
the third rule, Hund's rule of maximum multiplicity. Now what does this rule explain to us? It says pairing of electrons in the orbitals. We have orbitals in which the electrons are filled inside. That pairing of electrons in the orbitals belonging to the same subshell. See, when I say S subshell, it has 1 orbital. When I say P subshell, it has 3 orbital. D, 5 orbitals, and F subshell has got 7 orbitals. So in a subshell, there are different orbitals and the electrons are filled in each orbital, and that pairing will take place only when all the orbitals are singly occupied. Otherwise, the pairing does not occur. This is what is explained through the electronic configuration. When we write the electronic configuration, there are 2 methods. In 10th standard, you remember children, we used to write using SPDF notations. So when writing that, you must write the principal quantum number first, and then you should write the concerned subshell, that is S, P or D. The next one is through orbital diagram. When you are drawing the orbital diagram, you should make sure that you put the electrons with opposite spins, not in the same direction like this or like this. It does not make any sense. One with up-headed arrow, the other one with a down-headed arrow, which means positive and negative sign. Example, if you see hydrogen having atomic number 1, it is 1s1, you write only 1 up-headed arrow. When you have helium with atomic number 2, 1s2, so 2 electrons with 2 different arrows showing the opposite spins, which is Pauli's exclusion principle. So for understanding Hund's rule, we will be also seeing the filling of electrons in the orbitals.
Electronic configuration of atoms. In multi-electron atoms, the orbitals and subshells have different energies, and their relative arrangement is called an energy level diagram. In the energy level diagram, the orbitals with equal energy are called degenerate orbitals. Orbitals with the same value of the principal quantum number n have different energies for different values of the azimuthal quantum number L. Thus, the energy of the orbitals is determined by a rule called the n plus L rule. The rule states that lower the value of n plus L for an orbital, the lower is its energy. For 3d orbitals, the n plus L value is 5, and for the 4s orbital, the n plus L value is 4. Thus, in the energy level diagram, 3d is arranged above the 4s orbital. However, if two orbitals have the same value of n plus L, then the orbital with a lower value of n will have lower energy. For 3p orbitals, the n plus L value is 4, and for the 4s orbital, the n plus L value is 4. Thus, in the energy level diagram, 3p is arranged below the 4s orbital. On the basis of the n plus L rule, the sequence of energy of orbitals is summarized as shown. The increasing order of energy of orbitals is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d and 7p. The electrons are filled in the lowest energy orbital available. The distribution of electrons in different orbitals associated with a given atom is called the electronic configuration of the atom. The electronic configuration of an atom is represented in two ways: the SPDF notation and the orbital diagram. In the SPDF notation, the atomic orbital is written as a combination of the principal quantum number represented by a number, while the associated subshell is represented by the letters S, P, D or F. The number of electrons in the orbital is represented as a superscript. In the orbital diagram, the orbital is represented as a square box or circular box. Of the two types, the square box is the most commonly used representation of an orbital. Electrons are represented with the help of arrows. The direction of the arrow represents the spin of the electrons. The s orbital is represented by one box. The 3p orbitals are represented by 3 boxes, and the 5d orbitals are represented by 5 boxes. Filling of electrons in these orbitals is based on certain rules and principles. Let's take a look at these rules and principles in detail. The filling of electrons in the orbitals is based on the Aufbau principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. Click each tab to learn more. The Aufbau principle states that in the ground state, an electron enters the lowest energy orbital first, followed by subsequent filling of orbitals in increasing order of their energies. The energy level diagram for a multi-electron atom shows the increasing order of energy of orbitals. The first electron of the atom will enter the 1s orbital, followed by the filling of the 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d and 7p orbitals. According to Pauli's exclusion principle, an orbital can accommodate a maximum of 2 electrons with opposite spins. In other words, no 2 electrons in an atom can have the same set of 4 quantum numbers. The possible number of electrons in an orbital is 0, 1 or 2. Hund's rule of maximum multiplicity states that pairing of electrons in the orbitals of the same subshell will occur only once all the orbitals have had 1 electron each. For example, once all the 5 orbitals of the d subshell have had 1 electron each, pairing of electrons in the orbitals will occur. Consider the electronic configuration of a chlorine atom. The atomic number of chlorine is 17 and its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. The orbital representation is 1s and 2s orbitals filled with 2 electrons each with opposite spins. 6 electrons in the 2p orbitals are first filled by pairing of the 3 orbitals with 1 electron each, followed by their pairing. 2 electrons with opposite spins are filled in the 3s orbital. 5 electrons in the 3p orbitals are filled by pairing of 3 orbitals with 1 electron each first, followed by their pairing with the 3pz orbital with 1 electron only. Chromium with the atomic number 24 shows an exception. The expected electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d4. However, one of the electrons from the 4s orbital shifts to an empty 3d orbital to change the configuration to 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d5. This shifting of electrons gives rise to half-filled 4s and 3d orbitals, which are extra stable due to lower energy and symmetrical distribution of electrons. Thus, the half-filled and completely filled orbitals are extra stable, making S1, S2, P3, P6, D5, D10, F7 and F14 extra stable states.
So let us start filling the electrons and the orbitals now. Lithium with atomic number 3. We are going to follow Avogadro's law, Pauli's exclusion principle and Hund's rule. So 3 is the atomic number. We just do how we were doing in 10th standard. So 1s, 2, because S subshell can take 2 electrons to the maximum, and 2s, 1. So 2 plus 1 will become 3. So when I am going to fill it in the orbitals, it will be 1, 2. 2 electrons here, and this 2s is having only 1 electron. So beryllium with atomic number 4. It becomes 1s2, 2s2. So each orbital is having 2 electrons with opposite spins. That is Pauli's exclusion principle. Boron having atomic number 5 will have 1s2, 2s2 and the 5th electron go to the p subshell, as p subshell can take maximum 6 electrons. So it will be here 2 electrons, here 2 electrons, and in p subshell 3 orbitals are there, and the 5th electron enters my first orbital. Now when we come to carbon with atomic number 6, it is 1s2, 2s2 and 2p2. So 2 electrons in 1s, 2 electrons in 2s. Now we have to be very careful. Here we start following Hund's rule of maximum multiplicity. Now how does it work? Now p subshell has got 2 electrons. So I have here 3 orbitals for p subshell. So the 5th electron enters my first orbital.
And what does Hund's rule says? The pairing of electron does not take place until each orbital is singly occupied. So here I have 3 orbitals. The 5th electron enters my first orbital. I must not do the pairing. So what am I supposed to do? The 6th electron will enter my second orbital. So if you are going to count, it will be 2, 4, 5 and 6. So hope you are able to follow, children. So from carbon we will be following Hund's rule of maximum multiplicity. Children, now we will see nitrogen with atomic number 7. 7 electrons are present in nitrogen atom. So let's follow Avbau's principle. That is, the electrons are filled in the orbitals with their increasing energy. So with 7 electrons, S subshell will take 2 electrons, 2s will also take 2 electrons, and 2p, 4 electrons are already filled out of 7. So how many we need? We need 3 more electrons. So it becomes 2p3. So I am going to start filling in my orbitals. 2 electrons with opposite spins. Again 2 more electrons with opposite spins. And here p subshell is having 3 electrons. So it becomes 1, 2, 3. So these 3 orbital of p subshell are having 3 electrons. Please remember this structure. I will be asking you a question in the next. Now oxygen is having 8 as its atomic number. So here it will be 1s2, 2s2 and 2p4. So how do I fill my electrons here? It will be 1s2 here, 2s2, here it will be 1, 2, 3 and the 4th electron comes and does the pairing. So here the Hund's rule will be working with pairing of electrons in the orbitals. Now fluorine having atomic number 9, it will be 1s2, 2s2 and 2p5. So how does the filling take place? Here it is 1s2, 2s2, 1, 2, 3. I must start doing the pairing 4 and 5. Able to follow, children? Now the last one is neon with atomic number 10. So it is 1s2, 2s2, 2p6. So 2 electrons in 1s2, 2 more electrons in 2s2. So here it becomes 1, 2, 3, 4, 5, 6. So this is my completely filled orbitals which we which will be calling as core electrons, which you will be seeing in the next slide. And here it is half filled. P subshell is half filled. Here is also they are having more stability. So now I think you are able to follow the filling of electrons in the orbitals. You can start practicing with sodium till argon or also till calcium. It will be helping you how the electrons are filled in the orbitals.
Electronic configuration of elements. An atom is the basic unit of all matter, and an element is a grouping of the same type of an atom. Atoms consist of a positively charged central nucleus that is surrounded by negatively charged electrons in different orbitals. The term electronic configuration indicates the arrangement of these electrons within the various orbitals. According to the Aufbau principle, electrons will first occupy the orbitals of lowest energy. An s orbital, for example, will have lower energy in the principal energy level. The second rule is the Pauli exclusion principle. According to this principle, no more than 2 electrons can occupy a single orbital. When 2 electrons occupy an orbital, they must possess an opposite spin. And it can be clockwise or anticlockwise. The spin of an electron will be denoted with a vertical arrow. The third rule is Hund's rule. According to this, electrons will occupy orbitals of the same energy in such a way as to maximize their same spin direction. For example, the p orbital contains 3 orbitals of equal energy. In this case, according to Hund's rule, 1 electron will enter each orbital until all the 3 orbitals contain at least 1 electron with the same spin direction. and then they will pair with electrons spinning the opposite direction. Let's apply these rules to write the electronic configuration for elemental oxygen. Oxygen's atomic number is 8 and it consists of 8 electrons. According to the off-Bohr principle, the first electrons will occupy the 1s orbital. Because the 1s orbital can host 2 electrons, it follows Pauli's principle and accommodates 2 electrons spinning in opposite directions. 2 additional electrons will follow Pauli's principle and occupy the 2s orbital. Additional electrons will enter into the p orbital, and here they will follow Hund's rule. Initially, 3 electrons will occupy each sublevel of the p orbital, and the remaining electron will occupy the first sublevel. The resulting electronic configuration for oxygen is 1s2, 2s2, 2p4. Summary. According to the off-Bohr principle, electrons will occupy the orbital of lowest energy first. Pauli's principle states that no more than 2 electrons can occupy an orbital. Hund's rule states that electrons will occupy orbitals of the same energy in such a way as to maximize their same spin direction.
Off-Bohr principle. The filling up of electrons or in the orbitals or electronic configuration follows certain rules known as the Off-Bohr principle. This principle was formulated by Niels Bohr and Wolfgang Pauli. This principle states that electrons will first occupy orbitals of the lowest energy level. According to the Pauli exclusion principle, an orbital can hold a maximum of 2 electrons. According to the Hund's rule, orbitals of the same energy are filled with 1 electron each before filling with a second electron in an opposite spin. An atom has several shells around the nucleus in several quantum numbers. The lowest principal quantum number, n, is the nearest to the nucleus. Each principal quantum number has a principal energy level known as a shell. The principal quantum number 1 has 1 shell, S. Quantum number 2 has 2 subshells, S and P. Quantum number 3 has 3 subshells, S, P and D. Quantum number 4 has 4 subshells, S, P, D and F, and so on. Each shell or subshell has several orbitals. S shell has 1 orbital. P has 3 orbitals. D has 5 orbitals. And F has 7 orbitals, and so on. Let's observe how the electrons of magnesium filled up according to the Off-Bohr principle. Magnesium has 12 electrons. According to the Off-Bohr principle, the electrons will first occupy orbitals of the lowest energy. 2 electrons fill the first s shell, 2 more fill up the 2s shell. In the second shell, there is another subshell, p, with 3 orbitals. 1 electron moves into each orbital and then the second electron joins, making 2 electrons in each orbital, amounting to 6 electrons in p subshell. The remaining 2 electrons occupy the next higher shell, 3s. The electronic configuration of magnesium is 1s2, 2s2, 2p6, 3s2. In calcium, the electrons fill up the shells in the sequence 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. In the third quantum number, the subshells are s, p, and d. However, in the case of calcium, we can see that 4s shell is filled up after 3p instead of 3d. A simple Off-Bohr diagram explains the filling sequence of electrons. Summary. According to the Aufbau principle, electrons will first occupy orbitals of the lowest energy level, and an orbital can hold a maximum of 2 electrons. According to Hund's rule, orbitals of the same energy are each filled with 1 electron before filling any with a second.
So we have come to the last part, that is to know about the stability of the orbitals. See, before knowing about the stability, we should be knowing what are core electrons and valence electrons. When I take the noble gas elements like neon, argon, krypton, xenon, they will have all the electrons in the orbitals completely filled. So those electrons are called as core electrons. And the electrons which get added to the new quantum number again after a noble gas are called as valence electrons. So when we take neon with 10 electrons, these are core electrons. And from sodium I start adding sodium, magnesium, aluminium, silicon. So those are called as valence electrons. Now what are half-filled and completely filled orbitals having a role there? So when I take p sub shell, we know p6 is the maximum number of electrons, but their half-filled p3 becomes more stable. Similarly, d10 are stable, their half-filled d5 also becomes more stable. With f sub shell 14 the maximum electrons, f7 also becomes more stable. So p3, p6, d5, d10 and f7, f14 are the most stable orbitals. That is, we call them as half-filled and completely filled orbitals in an atom. That's why we studied 2 examples last year with chromium and copper. Chromium having atomic number 24. Instead of 3d4 and 4s2, they try to get 3d5 and 4s1, where the half-filled d5 becomes more stable. Similarly with copper, 3d9 and 4s2, it becomes 3d10 and 4s1, where 3d10, d10 completely filled becomes more stable. Why this half-filled and completely filled are stable? Because of the lower energy difference between 3d and 4s, the electron from the 4s jump to the 3d, which is a higher energy level, to get a stable configuration, or I would say to get a exceptional configuration for chromium and copper. So this is most important because although we follow the increasing order of energy, only the small difference is with 3d and 4s. That's how they show a different configuration with 2 elements. So with this, the chapter gets over, children. So take care. I'll be posting videos for you, and watch the videos. Take the notes wherever it is necessary. I'll be giving you a link with the previous solved the question papers also. So be on with the syllabus. If you have any doubts, don't hesitate. Kindly ask me, and take care. See you in the next class. Bye, children.